Hello and welcome to this Electrical Principles training video. This video is designed to be used in conjunction with the worksheet that you'll find the link to in the description below. So if you haven't already done so, please click that link, download the worksheet and then follow through the questions as we go. Have a go at answering them yourselves and then check your answers against the worked example that I'll show you on the board. So let's get started by answering question 1. So question 1 tells us that 3 identical resistive loads of 25 ohms are connected in star to a 415 volt supply. And we're asked to calculate the phase voltage, the line current and the phase current. So let's just put down the detail of what we already know. We're told that it's a 415 volt supply. So we know that the voltage between any two of those phases will be 415 volts. So between there and there, we've got 415 volts. With this kind of question, it's always a good idea to at least sketch out an image of what you're calculating. It'll just help you to formulate your thoughts and visualize what you're trying to do. We also need to list what the resistance of the circuit is. So here we can see that the resistance of this is equal to 25 ohms. So each one of those is worth 25 ohms. So we've got that clearly on the board. It's a good idea with this kind of question to always just do a little sketch of what you're calculating and to write down as much information on there as you can. So in this case, we already know what the line voltage and the resistance is. So we'll just make a list of the things we know. We already know that the resistance is 25 ohms. So R is equal to 25 ohms. And we know that the line voltage, VL, is equal to 415 volts. If this is new to you, this idea of line voltage and the other things we're going to talk about, phase voltage, line current and phase current, then please go and watch a previous video in this series on 3-phase because it's going to help you to understand the maths that we're about to do now. So at this stage, we'll write up what we're trying to find. So we need to know what the phase voltage is. So that's one thing that we're going to try and find. We also want to know what the line current and the phase current is. So we'll write those up as well. So we'll say that the line current and the phase current are equal to something. So we'll try and find the phase current and we'll try and figure out what the line current is going to be also. So we'll write that on there. IL is equal to. So those are the things that we're trying to find. So what calculations do we need to do to find those answers? Well, let's try and figure it out. First of all, we know the line voltage and we want to find the phase voltage. So this is really the first step to answering this question because we need to know what voltage is acting across the load so that we can figure out how much current is being pushed through the load. So here we're going to say that the phase voltage, let's calculate that. So the phase voltage will be equal to the line voltage, VL, divided by the square root of 3. Now again, if that formula is new to you, then please go and watch a previous video in this series because it'll help you to figure out where that's coming from. So all we've got to do is just put the numbers in. So we'll say that VL is equal to 415 volts and the square root of 3 is just a mathematical constant that stays in this calculation. So we've got 415 divided by the square root of 3. So we'll put that into our calculator. 415 divided by the square root of 3. And that's going to give us 239.6 volts. So we've got 239.6 volts. There we go. So we've figured out what the phase voltage is. So we'll put that in there. 239.6 volts. Happy days. Now we need to try and figure out what the phase current is. So this piece of information is absolutely critical now because we know that the voltage across that load, the phase voltage, VP, is equal to 239.6 volts there. And we want to know how much current is that pushing through the load. Remember, the current through the load is the phase current. So that's what we're looking at there. So let's perform the next stage of the calculation. We want to know what the phase current is. We know what the voltage being applied to that load is, and we also know what the resistance of that load is. So we can use those with some nice Ohm's law. IP is equal to V over R, bearing in mind that the V we're going to be using is the phase voltage, VP, because that's the voltage that is acting on the load by itself. So if we now put the numbers in. We've got 239.6, which is the value we just calculated, divided by that resistance of 25. So 239.6 divided by 25, we'll put that into the calculator. 239.6 divided by 25, and that gives us a value of 9.58. We'll round that off to amperes, 9.58 amperes. So now we know how much current is flowing through that load. It is 9.58 amperes. So we can fill that in here as our answer, 9.58 amperes. And now we want to know what the line current is going to be. Now, hopefully from a previous video, you remember what the relationship is between line current and phase current in a star connected load. We know that the phase current is the current flowing through the load, and the line current is the current flowing through any one of the supply lines. So we can now say, we can perform the calculation, IL is equal to IP, and that's pretty much the simplest formula that you'll ever use in electrical science, because line current and phase current are the same value in a star connected load. So we can now say that that is equal to 9.58 amperes. So that's a nice easy answer to do. We've got 9.58 amperes. And that is question 1 on this worksheet completed. So question 2 on the worksheet asks, the same loads of 25 ohms are now connected in delta to a 415 volt supply. Calculate the phase voltage, the line current and the phase current. So we've got the same loads, 25 ohms, connected to the same value of line voltage of 415 volts. And once again, we're going to calculate the phase voltage, the line current and the phase current. So let's follow the principles outlined in the first question. We're going to fill in what we know on the drawing. So we know that VL again is 415 volts. So we've got VL is equal to 415 volts. And we know that the resistors are each worth 25 ohms. So we know that this resistor here is 25 ohms. So we'll put that in there, 25 ohms. So that resistor has a value of 25 ohms. And now we can start to calculate the things that we need to find. So by putting in the information we already know, we know that the resistance is equal to 25 ohms, so we're happy with that. We know that the line voltage is equal to 415 volts. And once again, we're asked to find the phase voltage, VP. So the phase voltage is equal to something, we don't yet know what. The phase current, IP, is equal to, we don't know what yet. And the line current is equal to, again, we don't know what that's going to be. So we want to find that and figure out what that's going to be. So let's do some calculations. So the first thing we need to figure out is what is the value of the phase voltage. So once again, VP is equal to, now again, we're in delta, so the rules have changed. And in a delta connected load, we know that VP is equal to VL. So once again, we can do that lovely simple calculation where VP is equal to VL, which is 415 volts. So the voltage that we find across our resistor is 415 volts. So we can put that in. 415 volts there. And that of course is your phase voltage is equal to that value. So that's nice and simple as a starting point. The next thing that we need to find is our phase current. So our phase current, IP. Once again, using a little bit of Ohm's law, we've got V and divided by R. And again, this V is the phase voltage, the voltage across the load. So therefore, VP is 415 volts this time, divided by 25. And 415 divided by 25, if we just put that into our calculator, I should be able to figure that out in my head. I think it's 16.6. We'll just quickly verify that. 415 divided by 25 is 16.6. Happy days. So we've got there 16.6 amperes. 16.6 amperes. So that is the phase current. That's the current that is flowing through that load there. Now obviously the line current is the current that flows down the supply line, and the current that flows down the supply line splits off. Some of it goes that way and some of it goes that way. So the line current is going to be bigger than the phase current. How much bigger? Well, if you've not watched the previous video, then we'll tell you now. So the line current will be equal to the phase current multiplied by, importantly, that kind of really important number that we use for three-phase systems, the square root of 3. So the phase current times by root 3 will give us the line current. So if we perform that calculation now, 16.6 times by the square root of 3, we'll get our value of line current, sorry. So 16.6 times by the square root of 3 gives us a value of 28.75 amps. So there we've got 28.75 amperes. Happy days. So now if it was me, I'd just go back and just fill these numbers in here. So the phase voltage was equal to 415 volts. That's a nice easy calculation, that one. The phase current is equal to 16.6 amperes. So that's that one there, 16.6 amperes. And then the line current is equal to 28.75 amperes. 28.75 amperes. 28.75. So that completes question 2. We found all the information that we needed to, but just an interesting little point here. If you look at these systems, we've got the same resistors connected in star and then connected in delta, and look what happens to the current that flows into the system. So here we had 9.58 amperes, and here we've got 28.75. Well, what's the number that relates those two together? If we do 28.75 divided by 9.58, now bearing in mind we've rounded these numbers off, so there might be a little bit of variance here, but if we look at that, you can see that we come out with practically 3. So we can say that if you take the same load and connect it in star and then connect it in delta, the amount of current that flows into the system will be 3 times as much. So now let's answer question 3 of this worksheet. So in question 3, we're told that we have 3 identical resistive loads of 50 ohms connected to each other in star. So here we've got the resistance of this is equal to 50 ohms. So each one of these has a value of 50 ohms. And then the question tells us that those 50 ohm resistors are connected in star to a 400 volt supply. So that will be 400 volts there. So we've got a line voltage of 400 volts. So here's the things that we either know or are going to find. So the resistance in this question is 50 ohms, so we can put that in there. We've got 50 ohms, and the line voltage we know is 400 volts. So 400 volts. And now we need to find the phase voltage, the phase current, and the line current. So let's have a look at figuring out what these are. So first of all, we need to know what the phase voltage is going to be. So we say that VP is equal to VL divided by root 3. So we end up with 400 divided by root 3, and this should come up with a reasonably familiar number when we put this into the calculator. So we've got 400 divided by the square root of 3, which is equal to 230.9 volts. So 230.9 volts for that one, which is a nice value, which is instantly recognisable as pretty much the voltage that we state our single phase supplies at in the UK. So we've got 230.9 volts there. So we can say we've now found the phase voltage. We then want to move on and calculate the phase current. So the phase current is found by the following process. We just use a bit of Ohm's law. The phase voltage is obviously the voltage across the load. We know that from a previous video. And we know that to calculate the phase current, we use a bit of Ohm's law. IP is equal to VP over R. Notice we're using the phase voltage because the phase voltage is the voltage across the load. So that's the one that defines the current flow through the load. So we're going to do 230.9, which is what we just calculated, divided by 50 for our value. So we're going to do 230.9 divided by 50. So 230.9 divided by 50, and that's going to give us 4.618 as an answer. So 4.618 amperes. So there's our answer to how much current is going to flow through the load, 4.618 amps. And then to figure out what the line current is going to be, this really could not be any easier, because all we've got to do at this point is remember that in the star connected load, the line current, which is the current flowing into the circuit through any one of the supply lines, is exactly the same as the phase current, which makes sense because the current flowing through this load must be coming down this line here. So therefore we can say that the line current will be equal to 4.618 amperes. Happy days. So we'll volley that in there, 4.618 amperes. So that answers question 3 of this worksheet. So question 4 of this worksheet asks the same loads of 50 ohms are connected in delta to a 400 volt supply, and then we're asked to calculate the phase voltage, the line current and the phase current. So once again, just as we had in question 3, we've got a resistance of 50 ohms, so there's our resistor value, R equals 50 ohms, and the 50 ohm resistor has now been connected in delta in this system, and it's connected once again to that 400 volt supply. So the line voltage, the voltage between any two of the supply lines, is 400 volts. So listed down here, we've got all of the values that we're trying to find or that we already know. So we know that the resistance in this circuit is equal to 50 ohms connected across each phase. And we know that here we've got VL, which is equal to 400 volts. So that's 400 volts, which is going to go in there. We then need to calculate the phase voltage, the phase current and the line current. So we'll try and calculate those now. And again, the really nice, easy part about this to start with is that the phase voltage is exactly the same as the line voltage in the delta connected load. So we can say that the phase voltage is equal to the line voltage, which means that the phase voltage is equal to 400 volts. If only all maths were this easy. Yeah? So we can put that in there, 400 volts. We then need to go on and calculate what our phase current will be. And the phase current, remember, is the current that flows through the load. So it's dependent on the voltage that is applied to the load, and the voltage that is applied to the load is 400 volts. So we're just going to use some simple Ohm's law again. IP, the phase current, is equal to VP, the phase voltage, the voltage across the load, divided by the resistance of the resistor. So we've got there VP over R. So we're going to do 400 divided by 50, and I don't think it's really worth putting that into the calculator, is it? 400 divided by 50 is going to give us 8 amperes of current flow. So now we've found our current, and we can stick that in here, 8 amperes. Next, we need to find our line current, and if you remember from the previous answer, the line current is equal to the phase current multiplied by that very important number, √3. So line current is equal to phase current times by √3. So we've got 8 times by the square root of 3. And if you do that calculation, 8 times the square root of 3, you will get the answer to the line current. So 8 times √3, which is going to give us 13.86 amperes. So there we've got 13.86 amperes. So that's the answer to question 4. We've now found our line current, 13.68 amps. So we can see there that the resistance is 50 ohms, the line voltage is 400 volts, the phase voltage is 400 volts, phase current 8 amps, and line current 13.68 amps. So now let's answer question 5 on our worksheet. Question 5 states that 3 identical resistive loads of 220 ohms are connected in star to a 440 volt supply. So let's fill in the information that we already know. We know that we've got a resistive value here, R equal to 220 ohms, and we know that we've got that connected to a 3-phase supply, so we know that VL is 440 volts. VL is equal to 440 volts, bearing in mind that's the voltage between any two of the supply lines. So we'll fill that information up here as well. We know that VL is 440 volts, and we know that the resistance is also equal to 220 ohms. And the question asks us to go on to state the phase voltage, the phase current, and the line current. So let's work through this question and get our answers sorted. First of all, we need to find the phase voltage. So we're going to say that VP, bearing in mind that this is a star connected load, and we know that in a star connected load, VL divided by √3 will give us our phase voltage. So therefore we need to be able to stick these numbers in accurately. So 440 divided by the square root of 3 will get us to our answer. So put that into the calculator. We've got 440 divided by the square root of 3, and 440 divided by the square root of 3 gives us 254 volts. 254, we'll leave that. If we round that off to one decimal place, that's a 0, so 254 volts is perfectly acceptable as an answer. So there's our number, 254 volts for our phase voltage. Bearing in mind that the phase voltage is the voltage across the load, and therefore that is the voltage that we'll need to figure out what our phase current is, the current through the load, because the current through the load is dependent on the voltage across the load. So we move on now to start calculating the phase current, and that's really nice and easily done, because for the phase current, we're just going to use a little bit of Ohm's law. IP, the phase current, is equal to the phase voltage, VP, divided by the resistance R. So we're just going to put this into the calculation now, and we know that that will be 254, this value here, divided by 220. So 254 divided by 220 gives us an answer of 1.15 amperes. 1.15 amperes. Now that we know that the phase current is 1.15 amps, we can use that now to calculate what the line current is going to be. And again, if you haven't got the idea by this stage, hopefully we'll be able to correct you now. We know that the line current in a star connected system, so IL is equal to IP, and that's the end of the statement. Those values are the same in a star connected system. So therefore, our line current, IL, will be equal to 1.15 amperes. So we now know that the line current is 1.15 amps. Nice and simple. Okay, so now let's work out question 6 on our worksheet. And question 6 tells us that the same loads from question 5 of 220 ohms are connected in delta to a 440 volt supply. So we know we've got resistances here of 220 ohms, so we can just put that on the drawing, and we know that our line voltage VL is 440 volts. The only difference in this question being that we've got it connected now in delta instead of in star, so VL is equal to 440 volts there. So again, we'll put that into the information here. This is the part where I record what I already know from the question, 440 volts for the line voltage and 220 ohms for the resistance. And then I just make a note of the things that I'm trying to find, so that when I've completed all my calculations, I can fill this in and I've got my answers laid out nice and neatly. And if you can manage to structure your work in that nice, neat way, then your lecturer will love you forever. So let's have a look now at finding the first part of our question, which is the phase voltage. It's always nice to start off with an easy calculation, and in a delta connected load, VP and VL have exactly the same value. So there we've got the phase voltage will be equal to 440 volts. Nice, simple calcs there, no problem. Then we move on to start calculating the phase current, and the phase current, we rely on Ohm's law to find that. So IP, the phase current, is equal to V over R, but bearing in mind that the amount of current flowing through the load, which is the phase current, will be dependent on the voltage that is applied to the load, the phase voltage. So that's going to be 440 divided by 220. So you might have realised that there's a reason that I chose these numbers, because it makes this calculation really nice and easy. So we can see there that 440 divided by 220 gives us 2 amperes for our phase current in the delta connected system. What we then need to do, once we've filled that in on our list of definitive answers, is find the line current. And the line current is, there's a very simple relationship between the phase current and the line current. In a delta connected system, the line current, IL, is equal to the phase current, IP, multiplied by the square root of 3. So IL is equal to IP times √3. So we've got 2 amperes for our phase current, times by the square root of 3. And once again, if we put that into our calculators, 2 times root 3. So 2 times root 3, that gives us 3.46 amperes. 3.46 amperes. So we'll put that onto our list of definitive answers, 3.46. And there you can see that we've answered question 6 now. We've got our phase voltage, our phase current, and our line current. So all that remains in this video is to say thank you very much for watching.